There are also applications in economics of these rates of change that we have seen. For one of the examples is the notion of marginal costs. Okay, so let's say that we have a function c of x that gives the cost of producing x, well, let's keep it x units of a commodity. Okay, it could be chairs, it could be cars, it could be loaves of bread. Okay, so this is the cost function. Okay, and whenever we increase the number, so we increase from x1 units to x2 units, then the cost goes from c of x1 to c of x2. So then the additional cost is the increment of c. This is the additional cost. Okay. But then once we have the additional cost, we could also look at the average cost. Okay, so the average, we could actually look at the average rate of change of the cost. Okay, and this one would be given by cx2 minus cx1. What happened there? I'm missing a c. cx1 divided by x2 minus x1. Okay, the increase in the cost divided by the increase in the production. Okay, and of course, if we take, usually you will write this as increment of c divided by increment of x. Okay, but if we take an increment of x that is very small, what happens here? Let's say that the increment of x tends to 0. We get the derivative function at x. Okay, and this will be interpreted as the instantaneous rate of change of the cost. Okay, this is what in economics is called the marginal cost. You may object here that the increment of x may not be as small as in going to 0. Okay, this may not, given a particular problem, it may make no sense, but delta x could be small compared to x itself. Okay, let's say if you're producing 1 million cars, then one car is a small increment. Okay, going from 1 million to 1,000,001 is a small increment. Okay, and that is what this marginal cost is about. For example, this particular case, when you increment production by 1 unit and you want to know the corresponding change in the cost, okay, that is the marginal cost. So here what you could say is, well, C prime for a large number of items n is approximately equal to the increment Cn plus 1 minus Cn. Okay, here I would be dividing by n plus 1 minus n, but that is equal to 1. So we don't even write that. Okay. This is useful because instead it's much faster to compute. Okay, instead of computing Cn plus 1 minus Cn, you just compute the derivative and that's it. All right, so let's do a particular example. Let's say, for instance, that we have uh, a furniture producer, a furniture manufacturer, produces, let's say X tables, okay, per day. And the cost is given by Cx. Okay, and this function, the producer has already run the numbers, and it fits with the following polynomial: 1200 plus 50x minus 0.05 x squared, and these are dollars per day. Okay, so by spending this amount of money, gets X tables produced. All right, so right now they are producing 100 tables per day. And the question is, how much will the cost change by producing 101 tables per day? Okay, so what is the change in cost? Okay, so as we were saying, 100 is large enough. Okay, so we could say, okay, C prime of X is 50 minus 0.1 X. Okay, and because we are going from 100 to 101, then what we need to find is C prime of 50, which is 0.1 times 100, which is, this is 10, right? So we get 40. Okay, so this is the change in the cost. By producing one more table, the cost would go up dollars per item. Okay, so what we are saying here is that the marginal cost at the production level of 100 units is $40 per item. Okay, we are saying here every item that we want to produce extra when we are producing already 100 is going to cost $40.